What is it? Trusses. Okay? Before I start, trusses, let's see where we are. We started with equilibrium of rigid bodies, right? And we said the purpose of studying rigid body equilibrium was twofold. Take you back. You could go right behind that way. Okay. So finding the external forces, right? Support forces, and then internal forces. With rigid body equilibrium of frames, the objective was finding the internal forces at every single joint or the point of connection of the members, right? And what were the frame structures? They're connected together at any point along that member, not necessarily at the two ends. Loads can be applied anywhere. The joints that connect these different pieces can be pins, can be fixed. So these were the specific attributes of a frame. Trusses, in many respects, are much easier structures to analyze for these reasons. Okay? These are the attributes of a truss structure that you want to remember. Okay? First of all members are connected let me tell you what happens. In the previous section, the other section, of course, two people are also capturing these videos, and all the time we have right 15 minutes or 20 minutes past the hour, somebody stands up there, goes out, I'm not sure where they are going, probably using the bathroom or something, and then come back. So these videos have all these traffics also recorded, and I'm sure you don't like that. So I think I should give directions. All right, so all members are connected only at the end points. You cannot find in a truss that the members are connected somewhere along the length of that member. That's the first important attribute of a truss. Okay? All joints are pins. Okay? Somebody watching these videos is asking, well, what is this guy doing?
Exactly.
Okay. Loads, okay, act only at the joints. Or in other words, of course, we make the assumption in the analysis. Okay? These are major attributes of a truss, which makes it different from frames, right? Because necessarily in frames, members are not just connected at the two ends. You could have another member coming in, connected to a member somewhere, and you saw, for instance, the machine problem we did last time, there was no end connection. At the end, you were applying a force. All joints are not necessarily pins in a frame, and loads can apply anywhere along the member, right? So if that is the case, what conclusion you draw from these three attributes? Anybody can guess?
Everything's a two-force member.
Every member is a two-force member. Good. You deserve 2 points for that two-force members. Send me an email. So all members are two-force members.
But isn't that assuming that there's no force acting somewhere along the bar?
That is correct. That's what I said. Loads act only at the joints.
Oh, I did see the last
Right,
bullet
yes.
point. Sorry.
So every single member is a two-force member. With that said, there are two things that is important, and I would just jot them down here, and we'll talk about that you need to also be aware of in a truss. One is the concept of zero force member, and then the nature of the loading on a member, which is a member in compression or tension. We talk about these. First, let's share with you what is the main objective in the truss analysis. What was the objective in frame analysis? We wanted to find every single force that is connecting members of a machine or a frame together. In other words, the objective was to find the forces acting at those joints on every single member. That was the objective of a frame analysis. Some of these members would have been just two force members, right? If there was no load acting along that member, right? In a truss, knowing that all members are two force members, that means forces act along, so most 99% of the time, the members are straight members. So we know forces acting on a member from a joint will be acting along this member. Or in other words, member is a two-force member. So forces that are coming toward the joint from that member come along the line that connects these two ends or along the member, right? The analysis of trusses then comes down to the objective for the analysis of trusses is twofold, okay? Depending on the type of problem we are dealing with. Number one is you're asked to design a truss. By the way, how many of you have seen a truss structure? I'm sure all of you have seen it. You may not have known that's a truss structure. You've seen it. If you haven't, there's this timber lab here. Just look at that wall. You see a nice big truss that is that basically side of the structure. So first objective, and roof trusses, I'm sure all of you have seen. As a kid, you've been nosy enough to go into the attic, right? See what's going on there. And that's the structure that supports the roof. They look like this, right? Something like this, right? So you've seen that. We'll get to that. So first objective is in analyzing the trusses. I said in frames, the objective was find the forces that connect members together. In trusses, things are different. The first objective is sometimes you're asked to design a truss completely from zero, scratch. So you're told that build a truss structure that carries certain load. So you need to build a truss, and to build that truss, you need to know how much force each member of this truss will be subjected to. So the first type of analysis is that we want to find all member forces. And this is the case usually when you are designing a truss from scratch. Okay. The second type of analysis is that you already have a truss there. For some reason, maybe one or two members are deteriorating, rusted, broken, and you only want to replace those few members. You do not need to find forces in every single member of that truss. You want to find only forces in those members that you want to replace. Okay? So you want to find forces in one or a few members. This is the case which I call the repair, when you are repairing a structure. So in each of these cases, we use a different method. And that's why we teach these two different methods. In this case, we use equilibrium of joints, or we call this joint method of joints. In this case, you use equilibrium of a piece of a truss where that member or those few members that you want to find their forces are part of that section. So we call them, this method, equilibrium of a section or a section method. Okay, so we demonstrate both applications. Okay, so the first, just starting with this one, in frames again, going back to frames, in order to analyze a frame, you set up the free body diagram of every single member, right? And you remember the first 4 steps? You set up X, Y, break it apart, draw the free body diagram of each member, identify if there are any zero force members, then you start with a member with the least number of unknowns, find as many unknowns as you can, just move on until you've used all the free body diagrams that you need and to find all the answers. In the method of joints, which is the first approach, or the first analysis of trusses that we want to find, instead of looking at the free body diagram of members, we look at the free body diagram of every single joint in a truss. So in a way, in a sense, we are also taking the truss apart. But instead of looking at the free body diagram of the members, we look at the free body diagram of joints. If anybody can tell me why we look at the free body diagram of the joints, but not free body diagram of the members, in order to find all the unknown force members, forces, you will get 5 points right off the bat.
Since they're all 2 force members, it only connects at the points, or at the joint. So
Okay.
everything, the actual body of the member doesn't matter, it's only the reaction of the certain joint.
You're getting there. That's 75%.
Well, if it's a 2 force member, then drawing the free body diagram of the 2 force members doesn't really tell us anything.
Beautiful. So you get 3 points and you get 5. How about that? That's a good deal. All right. See, that's why. Because if you want to use like a frame, draw the free body diagram of members, you remember 2 force members, they don't give you anything. You've already used equilibrium to reach the conclusion that these forces act along the 2 ends in the opposite direction and they're equal. So you're not going to be able to find any, basically, unknowns from that free body diagram. However, if you have a joint, there are 2 or 3 members coming to that joint, so you have 2 or 3 forces in different orientations, and then you can draw the free body diagram and then write summation of forces along X and Y. Don't forget to send me the email. Okay. Okay. So that's what we do. Before we start the method of joints, as I said, there are 2 side notes that is important to know. I'm going to actually talk about this first and this one next. In frames again, you find forces acting at those joints and you're done, right? But in trusses, the story is different. Because all members are 2 force members, right? And the objective is that we want to find actually member forces acting on the members, right? Like the frames, we want to find forces acting on the members because members are what we are going to design. Who cares about the joint? You go to Home Depot and just buy a screw or bolt or whatever, I mean, that's the joint. We want to know how much force the member is subjected to, what material to use and what not, right? These members are either subjected to a force like this. These are 2 force members, right? Forces are acting along the line connecting the 2 ends. They can be either like this or like this. So in a design of a truss or finding the member forces, it is very important to know if the member is subjected to forces like this or like this. This means when this member is subjected to 2 forces that are pushing it in, that member is in compression. They're pulling it, it is under tension. Why is that important? Because truss may be made of different materials, and materials behave differently under tension or compression. For instance, concrete. If you have a concrete tube or whatever, right? Concrete is quite weak in tension, it's almost useless. But in compression, it's very, very strong. The opposite of that is a timber. very, very strong in tension, not so strong or as strong in compression. So depending, steel is the same. In compression and tension, maximum, basically bending stress or maximum failure stress, ultimate stress is the same. But so in other words, depending on what material you want to use, you need to know, not in this course, but maybe in the next courses, that what material to use, so you need to know the nature of that force. If I tell you this member is going to carry 400 Newton force, is useless. You should tell me, is that member going to be in compression or tension? If it's a huge force and it's concrete, I'm not going to use concrete, I'm going to use something else. But anyway, that's the reason. So that's this side note. What is this concept that we are going to be focusing on, and it is very important actually in truss analysis. As I said, in analysis of trusses, as you will see, we will start with looking at the free body diagram or the equilibrium of every single joint. As you do that, okay, in analyzing trusses, you may come across a case that you have this situation. You have a joint that these three conditions all exist. Condition number one is only three members come to that joint. Not four, not five, only three. Two of those members okay, are collinear. That is, somehow they lie along each other in the same line of action. Okay? And no external load acts at that joint. If that is the case, okay, these two members are collinear, the third member carries no load, and we call that a zero force member. In analyzing a truss, whether you're trying to use method of joints or sections, that's the first thing you need to identify. As you will see, I'll put it as in the outline of the procedure that I'm going to introduce, I would put that as the first step in solving a truss problem. Let me show you quickly, of course, I'm going to start discussing the analysis, but just to introduce this concept of zero force members. Let's say you have a truss which looks like this. And you have been asked to find all the member forces in this truss. Identifying the zero force member is the first step that you need to start, okay? And what does that mean? You look at this truss, find any joint that follows these criteria. Do you see a joint there? I'm sure you do. None of these, but right here. At that joint, only three members come together. There is no external load acting at that joint. Two of these are collinear. What happens? Let me show you first what happens. You're going to look at the free body diagram of this joint, right? Forces from these two members come like this, or the other way, it doesn't matter. And then you have this one. Of course, it doesn't have to be vertical like this, it can be like this in general. So if you have a situation like this, right, and you consider this is X, this is Y, right, Y, and X. If you write summation of forces along Y, this is the only force you have along Y. So if summation of forces along Y has to be zero, so this has to be zero. That's what we need. If you have three members coming together, two are collinear, and there is no load here, because if there was a load here, this would not hold true, right? No load acting, 2 are collinear, only 3 members. This one is always 0. If you have a 0 force member, that means for that loading condition, this member doesn't do anything. You can just simply remove that. So then you realize if you remove that, you have more than one zero force member. Because now the same conditions apply to this joint. 3 members coming together, no external load, 2 are collinear, so this one would go. When that one goes, now this joint is a 0 force member, right? And it's gonna go on in this particular truss like that, right? So you were asked to find all member forces, and you came down, instead of how many you had? 1, 2, 3, 4, 5, 6, right? 9, 7, 8, 9, 10, 11, 12, 13, 14. Instead of, oops. 14, no, let me tell you what happened. So that you don't feel it. As I was explaining, in the previous section, I do these, like here, video, and then people walk out, come back, or they come late. And so each time you see the shadow in front of the camera going. And so as people were coming in, I was actually trying to guide them to sit somewhere here so that they won't come. But I was facing toward the board. I didn't see that you were going that way. But anyway, so don't take it personally. But anyway, so that's it. That is the introduction, or all you really need to know to start the truss problems. Any questions before I begin? It's exciting. It's a very easy problem. Yes.
So I'm confused how, like, in that or on the example you have on your table, how the
This one?
Yeah, sure.
It's not a good example.
Well, how are the top and bottom? Is that one long piece of wood on the top and bottom? Or?
No. These are all separate members.
Oh, okay.
Right.
Sorry.
Each one is a separate. So the connections are only at the end, right? There's no connection here or no load here. Loads would apply only at these joints. Okay. So, yes.
So even if all it takes is just one side to be a 0 force member to.
That is correct. Good point. Good point. That's very good, important. You look at a joint. So if that joint satisfies these conditions, you can remove that member corresponding to that joint. And when it's gone, then the other joint would be, again, a new situation to start with. So, yes.
So, I'm just a little confused, because like for house trusses, like
Mhm.
in the roofs, they have those.
Very good point. That's in fact the question I was going to ask. Okay? So why do we leave those members there? Why do we need those members?
Because if they're theoretical pins, then once you remove that member, as soon as you load the frame would collapse because there's no.
No.
Okay.
Because if you put a force at where those connect, then it won't be a 0 force member.
See, you said it. 2 points. I think you deserve that.
Okay.
See, the 0 force members are not a property of the truss. They are conditions that resolves due to the type of loading that the truss in that particular loading case is going to carry. The same structure may be subjected to loads everywhere at every joint, right? We don't know. A roof structure is designed to carry all kinds of loads, right? One of these loading conditions may be that, okay, the only loads apply at 1 or 2 joints. So there are situations that you have a truss that you know for fact where exactly the loads might be. In that case, you don't need that force. And in that case, getting back to your point, you don't need to have that pin. You just make it, in fact, in this case, if these members are not needed, I have now just 3 members. I do not have what? I used to have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that 13-member trust is now reduced to actually a 3-member trust. Okay, so that's very important. Any other questions before I start? So with that said, we are going to start the last and final topic in the course. And I told you friction is a piece of cake. That's not a new topic. It's just an add-on. We'll cover that and it will be easy. Okay? This is the last important topic. Okay? So we will start truss analysis. And as I said, 2 objectives. One is the design or the method of joints. So first we'll discuss this maybe 1 or 2 days, and then method of sections. Like the frames, I like to introduce 7 steps. 7 is a good number to remember. Okay? So I would strongly recommend, again, not memorizing these, but this is a sort of a methodical, logical approach to solving a truss problem. By the way, I have actually a video course on truss analysis, both joints and sections, that I'll try to send you the link. I'll see, if Udemy allows that. I'll send it to you. Okay. So step 1 is very identical to frames. You need to always set up an XY coordinate system so you can identify whether forces are negative, positive, and so on. Step 2, in both method of sections and method of joints, which is what we are going to talk about, is identify, before you do anything else, identify 0 force members. Because you're asked, like that problem, solve for all member forces. If you start jumping into, let's draw the free body diagram of each joint and find all those member forces, is a waste of time. But once you identify 0 force members and remove them, the number of operation or solutions that you need to come up with can be reduced drastically. Okay? Step 3. Okay? In frames, you start with breaking the entire structure apart and draw the free body diagram of each piece. In trusses, you basically start with drawing, or not actually drawing, identifying a joint with minimum number of members coming to that joint. There you start with drawing free body diagram and then identify the free body diagram with the least number of unknowns. Here, before anything else, you identify a joint with the minimum number of members coming to that joint. Okay? And step 4, you draw free body diagram of that joint. Okay? Step 5, okay? Solve for all unknown member forces connected to that joint. Okay? Once you're done, go to the next step. Okay? Okay? Go to the next joint with minimum number of unknowns. Okay? And step 7, repeat until you have found all unknown member forces. Okay, you're done. Okay, 7 easy steps. You've noticed something. Some of you may have noticed something, right? You remember in frames, for the most part, almost all the time, you worried about finding also external reaction or support reaction forces. As you notice, in trusses, necessarily, that's not part of the steps that you need to follow. You may or may not need them, depending if a support joint has the minimum number of unknowns to begin with. If not, who cares? Why should you find it? Or if the support reactions are such, which happens at times, that you may have to do that. But we'll talk about that. But that's not a necessary condition to solve a truss problem. You don't have to find reaction forces. So let's demonstrate that through an example. Okay? Obviously, I will start with an easy problem first so that we can finish it. And of course, then we will go ahead and find other examples. Okay? So I'm going to start with this example. Very good problem. 15 kilonewton. Here is A, B, C, D, F, G, H. Okay. See. I meant this to be the same, so let's say I will do a correction here. So this is also 12 meters, 12 meters, 12 meters, 12 meters, and this one is 15. Okay. So this is a good example of a joint method. Problem statements are like this. Find all member forces. Remember, as we will see, those two sub notes or footnotes that I said, zero force members and compression and tension. When you find member forces, you do need to identify whether a member is in tension or compression, right? As I said, because it's made, depends on what material they're going to be made of. So step number one. Number one, easy. This is X, this is Y. Step number two, identify all zero force members. Why, if you look at it, if I skip that step, what happens? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members. Now let's see, do I have to really find all those member forces? Or no, you don't have actually 13. So do you see a joint with only 3 members coming together? two collinear, no load at that joint. H, look here. No external load. These two are collinear and there are only three. So this one carries no load. Right? And you know what, right? I showed you basically, right? So this is gone. As soon as you remove that, you notice that C follows or satisfies the same conditions. No load acting externally at C, two of the members are collinear, therefore this is gonna go. So once that is gone, joint G has the same criteria, follows the same conditions or criteria. Three members coming together, no external load, two collinear, this one and this one, so this is gonna go. Once that is gone, same thing applies to joint B. Three members coming together, no external load, two are collinear, so this is gonna go. This is a zero force member. Okay? So with that, I have now 1, 2, 3, 4 members instead of 13 members to find. So that's, so zero force members. Okay? So step number 3, now you go to a joint with minimum number of unknowns. How many unknowns I have here? If I consider these, okay? This joint has only 2 members. This joint has 1, 2, 3. This, but there's another unknown here, so 3 unknowns. I mean 4 unknowns. This joint has 1, 2 members, but also these 2 unknowns, so 4 unknown forces. At this joint, I have 3 members, there are 3 unknowns. So obviously, I will start with this. So I would write, look at the free body diagram of this joint. This is the external load, 15 kilonewton. There is a force like this and a force like this. This is the force of, these don't matter anymore. This is just one member now. So I'm just gonna call this member AD. This, I call that member FD. So now, draw the free body diagram, right? So this is step 4. Okay, this was step, I would consider this step 3 and 4 that we've done. Now go to step 5 and solve for all these unknowns. So all I need is just to write summation of forces along y is equal to 0. If you look at this, this is 15, and this is 15, this is 36. Actually, I wanted to make it such that it would be more meaningful, but that's okay. So that'll be 5 and 12, that's okay. So this becomes 5, 12, so it's 144, 25, 179, I guess, right? Or 13, yeah. Right, square root of 13. Okay, so summation of forces along y is equal to 0. You will have 5 over 13 times force in FD, okay, minus 15 is equal to 0. So F of FD then is equal to, okay, this cancels out, would be 5 times 13 or 65 kilonewton. Am I done? Came out to be positive, that means the assumed direction is correct. Do I need to do anything? The answer is incomplete. This is only half the answer. You need to identify whether this force is exerting a compression force on the member or a tension force. Remember, these are forces coming from those members acting at that joint. Who cares about the joint? I want to know about this member force. So the member force is this. This is FD, right? Because if this is a force from the member acting on the joint, on the corresponding member, at that point D, you have a force like this. This is a two-force member, so you also have FD and the other end. So that member then is in compression, right? Let's do the other one. Now let's write summation of forces along X is equal to 0. So you have FAD plus FFD times 12, so you have 65 times 12 over 13 is equal to 0, right? So you have 12 divided by 12 times, it would be 60. It would be negative 60. That means what? The assumed direction is wrong. Yes?
Isn't that 39?
Which one would be 39?
Yeah, because you add 15 divided
Which
by
one,
5
39? This one
over there. Or it's not 65 kilometers.
would be 39, really?
Because 15 divided by 5 is 3 times 13 is 39.
Oh, 39 then? Okay. So 39, so this one becomes 39, so it would be 3 times 12, so it would be 36, right? Okay, kilonewton. But it came out to be negative. That means what? The assumed direction is wrong. So very similar to what we had before. We started with an assumption. The assumption was wrong, so I have to make a correction here. Okay? So that means we're going to get rid of that. But look, this is the force coming from this member acting at this joint. So member AD, okay, this member AD, would be what? At this joint D, then you have a force like this, right? Acting on that member. That means on the other end, you have this. So this member is in tension. So you need to put that next to this. And now you have a complete answer. But from this observation, you can draw a simple conclusion that each time you don't have to do this. And you can call it a rule of thumb or whatever you want to call that. But as you make the observation, if the member exerts a force on that joint that is coming towards the joint, the corresponding member is in compression. If it's moving away from the joint, the corresponding member is in tension. So when you do the joint analysis, if the force of the member is towards the joint, that member is in compression. If it's going away from the joint, that member is in tension. So you don't have to draw these all the time to figure that out. Just remember towards, away. That's it. Okay? So now that you're done, you just put a check mark on all those members that you have found and move now to step 6. A joint with minimum number of unknowns. Here, if you look at this joint, this is known, you have 2 unknowns. Here, you have this known, but you have 1, 2, 3. Here, 1, 2, 3, 4. So obviously, I'm going to use this one. So I will go as a step 6. Okay? I will go to the member with the minimum number of unknown, which is joint A. I know that this member AD is in tension, so the force on joint A would be like this. So this is the force AD. I don't know what directions these are. I'll just make it up. Intentionally, I'm going to assume it's like that. So this is the force of EA. This is the force of FA. Okay? And this is 5, and this is, so this slope here, okay, this is 4, and this is, oh, I'm sorry, this is 3, 4, and 5, right? Divided by 3 would be 5, divided by 3 would be 4. So it would be 16 and 25, so it would be square root of 141. Okay? So this is 5, 4 square root of 41. So again, you write summation of forces along x is equal to 0. So you have 4 over square root 41 f of EA plus f of AD, which we know that is 36. 36 is equal to 0. So who's going to help? Give me this number. 36 times square root of 41 divided by 4, and it's going to be negative. 36 divided by 4 actually would be 9. So just 9 times square root of 41. About 60 something. 57.6. So how about, let's say, 58? Yes.
When you're isolating the joints, can you just draw the forces either all towards or all away? And then
Good point. You can draw in any direction, like the frame analysis. You can draw them at any direction you want. When it comes out to be negative, that means the assumed direction, obviously for this, was wrong. So similar to frame, you have to make that correction before you go on. Correction here is even more important because that tells you whether there's a compression or tension. So in this case then, this is obviously going to be in tension. Okay? Now you write summation of forces along y is equal to 0. So you have f of FA, right, minus 5 over square root 41 times 58, okay, is equal to 0. So f of EA comes out to be how much? 58 divided by square root 41 times 5.
FA.
F of
FA,
FA, I'm sorry.
bottom.
Right. Yeah, this is FA, right? So I have it. So how much? How much? 45? 45. Let's say 45. Kilonewton. It came out to be positive. That means this is correct. Direction is correct. Since it is moving towards the joint, the corresponding member is in compression, right? So you found this and you found this, right? Now you have this joint with one unknown, this joint with, with two unknowns, this joint with 1, 2, 3 unknowns. So I'm going to use this one, right? So then you go to joint F, you have this force, you have this force. Actually, let's see what direction they were. FA was compression, so that is correct. And this one was, FD was compression, this one was compression, this one was also compression. And then you have this, and you have this. You have this, you have this. You have only two unknowns, which you can find. And once you find that, you end up with a joint that you never used and you did not have to use.
Fantastic.
Okay, yes.
If the assumed direction is correct for FA and like FBA, I believe, say the opposite of FBA is like pointing towards the other joint, so would that be compression and that would
No,
be
see, FA is moving that way. So the
sound like
corresponding
you're in
member,
it.
the force would be, at that tip of that member would be this way, and this end would be this way, so it would be in compression. So if the force coming towards the joint, the corresponding member is in compression. If it's away from the joint, the corresponding member is in contraction. Great. See you on Wednesday.